Well, welcome back. We've got a fun topic tonight, and this is titled Approximating a Definite Integral Using a Riemann Sum. Okay, and here's just a quick snapshot of Bernhard Riemann, the German philosopher who discovered this. So the first thing I need you to jot down is, what is Riemann sum doing? It's approximating the area under a curve. And when you hear Riemann, I want you to think rectangles. Get those R words in your head. We will do another shape eventually, but I want you to think rectangles as we get going here. So this first bunch of slides here, I don't need you to copy down, I just need you to pay very careful attention to. So, this first function, I just grabbed this off Wolfram Alpha. You can see is the function of x squared. Okay, so there's y equals x squared. I went on the x-axis from 0 to 6. And what I did is I built two rectangles in to approximate the area under the curve. Now this is specifically called a right-hand Riemann sum because, as you notice, if I go up on the right-hand corner of the rectangle is on the curve. If I go up on the right here, the right-hand corner of the rectangle is on the curve. So what this did is it approximated the area under the curve. Now, as you can see, this is very much an over approximation. Look at all this extra area that was accounted for. That is not under the curve. So you can see here the actual area is 72, and the approximated area with a Riemann sum is 135. It is very far off. Now again, please don't copy this down, but I did the same function, and instead of just putting two rectangles in, you can see I put 10 rectangles in. And I did a right-hand Riemann sum, so it's up on the right, over, up on the right, over. So it's still this over approximation because there's this extra area above the curve. But you'll notice, look how much closer I got when I put 10 rectangles in versus 2. I'm now at 83, which is a little closer to the actual area. Then I tried 50 rectangles. Okay, so again, I put 50 rectangles in between those two values from 0 to 6, and my approximation again got closer. It's still over, you can see how that's above the curve, but it's much, much closer. Then I got a little wild and I put 100 in just to see what would happen, and again, I went from an area of 74 to an approximated area of 73, so I got closer again. And lastly, I went just crazy and I put 500 rectangles in, and it took a few moments to calculate, but the area is almost getting to be close to that actual area. So one thing you can take away is the more rectangles you put into the Riemann sum, the closer your approximation will be. So I do want you to pause it, and we are going to put this one in our notebook. It says the graph of the function f is shown below. Approximate the integral from -2 to 4 of f of x using a right-hand Riemann sum, specifically with 3 subintervals of equal length. So the 3 subintervals are telling you how many rectangles you're going to put inside. The right tells you which side should touch the curve. Okay, so I would make these notes to yourself, touch the curve. And the subintervals of equal length is very important. Eventually we'll talk about ones that don't have equal length. So let's just highlight those 3 things for ourselves, and then it says sketch the graph of the right Riemann sum. So the first thing I want to do is figure out how big the base is going to be, and here's how I do that. The width of equal subintervals is equal to the width of the interval divided by the number of intervals. Okay, so the width of equal subintervals is the width of the interval divided by the number of subintervals that you want. So how big does my interval go from? Well, it goes from -2 to 4. So the distance from -2 to 4 minus -2, is a distance of 6. And I want 3 subintervals, so I'm going to take that distance of 6 and divide it by 3. Therefore, each of my bases are going to have a width of 2. Okay, so I'm going to go to my picture, and I'm going to start at -2, and I'm going to have a width of 2. So here's my first width of my rectangle. It has a width of 2. Then I'm going to do another color. Here's my next width of 2. And let me pick one more color and get a nice width of 2 in there. Okay, so now my goal is to build a right-hand rectangle. And all that means is when you draw the rectangle, you are going to touch the curve on whatever side it describes. So I'm going to touch the curve on the right side. So I'm going to go back to my red line here. I'm going to go straight up until I touch the curve, and then I'm going to go over to create the rectangle. Let me do the same with the blue here. I'm going to go to the right-hand side because it's a right subinterval. I'm going to go up until I touch the curve, and then over to create the rectangle. And I'll do the same with the purple. I'm going to go up till I touch the curve, which is right here. So I basically have 0 area here because I'm not going up at all. I'm touching the curve right there. So now my goal is to approximate that area using these rectangles. So all I'm literally doing is saying the area of a rectangle is base times height. So this is a base of 2 and a height of 1. So this has an area of 2. My blue guy has a base of 2 and a height of 1, 2, 3, 4, 5. So this has a height of 10. And then I have no area in my purple one. So my approximation, if I add up all my areas, I can say this is the integral from -2 to 4 of f of x dx is approximately, notice the approximation sign, 10. So again, it's not the exact area, it's an approximation. That's what a Riemann sum is doing. Okay, so this time it's the same function. We're going to approximate the area, and this time we want to use a left is the keyword Riemann sum with 3 subintervals. So again, I'm going to say it's 4 minus -2. That's a distance of 6, and I'm dividing it by 3 subintervals, so I know each of my widths or my bases of my rectangle will be 2. So I'm just going to do it into different colors again. So here's my first one, my blue width of 2, my red width of 2, and I'm going to go yellow. Now the key is that it's a left Riemann sum, so you are going up on the left-hand side until you touch the curve. So here was my blue base. I'm going to go up on the left until I touch the curve, and then come over and make a rectangle. We'll do the same with the red. We're going to go up on the left until we touch the curve, and then just come over and make my rectangle. And then same with the yellow. Up till I touch the curve and over and make a rectangle. So now my goal is to find the area of each of those. And again, it's just base times height. It's just a rectangle. So my blue looks like it's 2 by 1, 2, 3, 4, 5. So I'd say this area is 10. My red is 2 by 1, so a nice area of 2. And my yellow looks like it's also 2 by 10. So it looks like the approximation of that area is 22. So again, not the actual area, just an approximation. All right, our third Riemann sum is still a rectangle. This time it's specifically a midpoint Riemann sum. So again, my bounds haven't changed. I just want to be clear. I'm doing 4 minus -2 over 3 subintervals to get a width of 2. So again, I'm going to draw my widths out in 3 different colors just to recognize them. Now here's where we're going up on. We're going up on the midpoint. That's where I want to touch the curve. So as I follow, here's my yellow line here, I'm going to go up in the middle till I touch the curve, and then I'm just going to go from side to side to create the rectangle. So again, the blue, I'm going to go up in the middle till I touch the curve, and then just go side to side to create the rectangle. And again, the red, go up in the middle until you touch the curve, side to side to create that rectangle to approximate this area. So my yellow is 2 by 2, which is 4. My blue is 2 by 3, 6. And my red is 2 by 4, which is 8. And hopefully I can add correctly, and I get an approximation of 18. All right, so here I'm going to draw a bunch of little pictures, and again, our goal is just to approximate the area. Is it greater than, less than, or equal to the area? And that's all I'm concerned about. So in this function, I just want to make a note that it's increasing, and you'll notice it's concave down. So let's just jot those 2 things down. My left-hand Riemann sum. When you're going to approximate these, you don't want to draw in a million rectangles if you just want to know if it's greater than or less than. It's easiest if you just draw one in, and I make it fairly large. So I'm going to go up on the left, touch the curve, and over and down. And you'll notice this is clearly an under approximation. So the Riemann sum is less than the actual area. If I did a right Riemann sum, I'm going to go up on the right, I'm going to make one big one, go over and down to make my rectangle, and you can clearly see that the Riemann sum is an over approximation, so it's greater than the area, the actual area. In these next 2 pictures, just take note that the functions are decreasing and concave down. So if I were to draw a left, again, I'm going to go up on the left till I hit the curve, make one big rectangle. I can see that that's an over approximation, that's greater than the actual area. And if I do a right, again, one big rectangle, that is less than the actual area. This time I'm decreasing and concave up. So again, a left, looks like an over approximation, and a right and under approximation. And lastly, if I'm increasing and concave up, a left is an under and a right is clearly an over. So we're going to switch gears from the graphs and tackle a Riemann sum in a different method. You can see I have a table here, and this is called the tabular method. Obviously from the word table. Okay, this is the tabular method. So school carnivals hold raffle tickets at a fundraiser between noon t equals 0 and 8 p.m. t equals 8. The number of raffle tickets sold is modeled by this differentiable function, so that's key that it's differentiable. And they're telling you that it's r double prime is less than 0, so they're implying the function is concave down. Okay, so here's my table. You do need to copy the table into your notes here. Use a right Riemann sum with 4 subintervals to approximate the integral from 0 to 8 of r of t dt. Now notice they didn't say equal subintervals, equal being the key word. Your bases do not have to be equal. And that's what I want to highlight, that these are not equal bases. So here's how you do it. You need 4 intervals starting at 0 and ending at 8. So basically keep in mind, this is your x values, this is your y values. This is how you should mark it on yours as well. I'm going to go from 0 to 2, there's 1 interval. Pick it up where you left off, so 2 to 5, 5 to 6, and 6 to 8. Now again, those bases are not equal, but I'm putting in 4 rectangles, and wherever I finished, I started the next one. I finished at 5, started the next one. Finished at 6, started the next one. Okay, so I'm not going to sketch this out every time, but I will start a quick little sketch. The first blue rectangle here goes from 0 to 2. So basically, my rectangle goes from 0 to 2, and that represents my base. And now I'm going to draw in my height. And since it's a right Riemann sum, I'm going to pick the height are my y values, on the right. So if this is my rectangle, the height on the right is 5. Y value is the height, number on the right. Left, right. Height on the right is 5. So I'm basically going up 5 and making a rectangle. My next one goes from 2 to 5. So from 2 to 5, I'm going to go up on the height on the right, which is 9. So I'm going to go up to 9 and make a rectangle. And you could draw this out, but it is really not necessary. You basically just have to ask yourself, what is the base and what is the height of each rectangle? So the base of the blue one, if I went from 0 to 2, that's a distance of 2. The base is 2. The height on the right is 5. Plus, now I went from 2 to 5. The difference between 2 and 5 is 3. The base is 3. The height on the right is 9. The next one went from 5 to 6. That difference is a base of 1. The height on the right is 10. Plus 6 to 8 gets me a base of 2. And the height on the right is 11. So I've got 20, no I don't, 5 times 2 is 10, plus 27, plus 10, plus 22. So this approximation is approximately 69. Okay, so now we're going to approximate the exact same thing, but this time we're going to use a left-handed Riemann sum with 4 subintervals. So again, I'm going to break it up from 0 to 9, 4 subintervals. And again, the bases are not equal. It doesn't say they are. So again, my base from 0 to 2 is a base of 2. And this time I need to pick the height on the left. Well, again, this is the left and right of this interval. The height on the left is 0. Plus the next base, 2 to 5, has a base of 3. And the height on the left is 5. Plus the next base, 5 to 6, is 1. And the height on the left is 9. Plus the next base, 6 to 8, is 2, and the height on the left is 10. So that's going to get me 0 plus 15 plus 9 plus 20, which looks like 44. So same table. This time, however, we're going to calculate a midpoint Riemann sum. Now notice what they changed on you. They changed it to 2 subintervals. Okay, so I have to go from 0 to 8, and I'm only going to have 2 subintervals. So I'm going to break it up. So I'm going to go here to here. So that's basically 1, 2, 3 boxes. And then here to here, 1, 2, 3 boxes. Now again, they're not equal bases. I'm just breaking it up to the same number of boxes, so to say. Okay? So my base this time, from 0 to 5, has a base of 5. And this time I want to pick the height in the middle. So from 2 to 5, the height, again, x and y is my height. The middle height is 5. Plus the next base, 5 to 8, so that's a base of 3. And the height in the middle is a height of 10. So I've got 25 plus 30. I get an approximation of 55. Okay, so this time we want to approximate the integral from 0 to 20 of x squared. Now we can find the actual area. So I just want to be clear, when you integrate, you get the actual area. So if I go x cubed over 3 from 0 to 20, that's 20 cubed over 3 minus 0. 20 cubed over 3 is the actual area, which is 2,666.6 repeating. Now again, a lot of times you don't want the actual area, you just want an approximation, and that's what they're asking us to do. So they're saying using 4 equal subintervals and a right-hand Riemann sum and a left-hand Riemann sum, let's approximate the area. Okay, so the first thing I want to do is figure out the width. Notice it said equal subintervals. Okay, so my width, like we talked about before, is I just find the difference in the bounds and divide by the number of subintervals. So I'm going to say I have a width of 5. Okay, and I actually find it easier to make a table of values here. So I know my width is 5, and I'm going to go from 0 to 20. So 0, 5, 10, 15, 20. Okay, they all have a nice width of 5, and there's my 4 subintervals. Now I need to get their heights. Well, we've been practicing finding heights in triangles for a while now. So if I want the heights at 0, I simply plug 0 in to get the height. 0 squared is 0. At 5, 25. At 10, 100. At 15, 225. And at 20, 400. So I can easily make my own tabular chart very quickly. And then I'll just go ahead and calculate a right and a left. So I'm going to use RRS for right-hand Riemann sum. And I'm going to say, okay, find your bases. So the first base is 5. And the height on the right, so if I'm looking at this, my right-handed height is a height of 25. Plus my base of 5. The height on the right is 100. Plus my base of 5. The height on the right is 225. Plus my base of 5. And the height on the right is 400. And then again, I could calculate the area. You could pull out that 5 because you know they all have equal bases and really just say 25 plus 100 plus 225 plus 400. If that math is easier to do, which it might be, in fact, if you don't have a calculator. Let's do a left-hand Riemann sum. So I'm not going to calculate it out. That's pretty straightforward. But let's talk about the left. So again, all the bases are going to be 5. So I'm just going to pull a 5 out, and I'm just going to go through, and I'm going to pick the heights on the left. Okay, so here's my first rectangle. The height on the left is 0. Plus the second rectangle, the height is 25. The third rectangle, the height is 100. And the fourth rectangle, 225. And again, I would add that and multiply by 5. All right, so last question to practice. Water's pumped into a swimming pool at the rate of P of T cubic feet per hour. The table of values below is strictly monotonic. That means it's only doing one thing. In this case, it looks like it's only increasing for the selected values of T. So we're going to write 3 things out. We're going to write a right hand out, a left hand out, and a midpoint out. And the key is we want 3 subintervals. So again, this is like my X and my Y. I'm going to carefully break it up into 3 pieces in basically the same number of blocks. So I think I can go from 0 to 4, that's 3, 4 to 8, and then 8 to 12. Okay, so again, they're not equal bases. They're not necessarily equal bases. I'm doing 3 blocks, 3 blocks, 3 blocks. Okay, so a right-hand Riemann sum. The first base goes from 0 to 4, so that's a base of 4, and the height on the right is 20. The next base goes from 4 to 8, so a base of 4. Height on the right is 30. And the next base is a base of 4. Height on the right, 55. Okay, so let's set up a left-hand Riemann sum. Now, we already know the bases are all the same, so we can pull that 4 out, and we can just pick the heights on the left. So 0, 20, and 30. And again, approximate that area. Lastly, let's hit that midpoint Riemann sum. Okay, so again, the bases are all 4, so that makes it nice. Now I'm just picking the heights in the middle. So the middle number is 2, but its height is 12. Middle number is 6, but its height is 25. Middle number is 10, and a height of 50. Okay, so again, we would just approximate that area. So we've covered almost all the different types we shall see, and we'll have some great practice tomorrow.